tired of looking at this right-handed world.
So good morning, everyone, and welcome back.
I guess that works.
Yeah, it's a little weird, but
It's 11:10. Let's start. My plan is to keep recording these for whatever they're worth, and keep posting them. I know that the sound is not probably the best. Today I tried to position it so we get the whole thing. Last time I was in a rush, I didn't, you know. I think some of you already viewed it. So, yeah, I will continue doing it. My tripod is fairly cheap and weak, so until somebody steps on it and breaks it, we will keep doing it. And then we have to wait till I order another one. Okay, let's see. So last time we started chapter 18 and we kind of went through it. Chapter 18, if you remember, we talked about temperature scales, right? And we started the ideal gas law. And we said PV equals to nRT, right? Ideal gas law? P equals to nR times T. The pressure, the volume, what is N? The number of moles are universal constant, and T is the temperature. So in what units is the pressure? Pascals. Pascals, or which is newtons per square meter, right? Force per unit of area. The volume? Cubic meters, yes. N is the number of moles, so moles. R is 8.31 in whatever units to make the left side and right side agree. And capital T is the temperature.
yeah.
And in what units? Kelvin, yes. Don't use degrees Celsius. Yes. So, yeah, so that is that. And now I want to write this in terms of a different unit. So this one counts the number of moles. And I want to write it as the number of atoms themselves, the number of atoms or particles. So remember that the number of particles will be, if you have 1 mole, what's the number of particles? 23, great. So it's however many, if you have 1 mole, N is 1, so however many moles you have, multiplied by Avogadro's number, right? And that will tell you the number of particles. Therefore, this little n will equal to capital N divided by Avogadro's number. And let's substitute it here and see what we get. So we get PV is equal, and usually P is lowercase in our book, and equals to nRT, but N is capital N divided by NA times R times T. I'm going to group them so that the R is divided by NA. We have N, R, NA times T, right? And so if you divide R by NA, it's called Boltzmann's constant. So it's called KB, Boltzmann's constant. And it's equal to R over NA. And R is 8.31, and A is approximately 6.02 times 10 to the 23. If you do this, 1.38 and 10 to the minus 23 joules per Kelvin. Yeah. So in other words, the ideal gas law can be written in the following format. N, the number of molecules or particles, KB, times the temperature. That's another way to write it. Which one should you use? Well, it depends. They're equivalent, they're equal to each other. If you're given the number of particles, then you use this one because you already have the number of particles. Why would you change from number of particles to moles only to use this one? Yeah, so it just depends on the actual situation. So I think we did an example, and I want to do another one. It's from the book. You have a cylinder of gas at T equal to 0 degrees Celsius. We have gas at T equal to 0 degrees Celsius. here is a gas. It's in a, always our gas is in a cylinder that has some kind of a piston. And we want that piston so that we can compress our gas or we can expand it, make the volume smaller or larger, okay? And we usually ignore the friction. We say the piston is friction, so we don't want to deal with friction, okay? So the gas is here, and and it is at T equal to 0 degrees Celsius. And what we do is we compress the gas. We press it so that the volume becomes half of what it used to be. So you pressure it so that the piston used to be here, and now it's here. Right? Compress it. So this is, let's call this V final, and this is V initial, and we're told V final is equal to 1/2 of V initial. Okay? And they also tell us that the pressure is 3 times what it used to be. So V final, P final is 3 times P initial. Okay? 3 times P initial. And the question is, find the temperature. What is T final? So T initial is 0 degrees Celsius. Is this a good unit to put into the ideal gas law?
No.
No. So it's 273, right? You add 273. So it's 273 K, right? Change from degrees Celsius to K. Add 273. And the question is, what is T final? Right? Should we go to Newton's laws to do this? No. You definitely don't want to use Newton's law. And Newton's laws, if you're dealing with one object, but collectively you have 10 to the 23, it's just, there's no way. So your friend, or our friend, would be the ideal gas law. The ideal gas law says PV equals to nRT. It's up to us. Is the number of molecules changing? Or I should point to this, that's the number of molecules. Or the number of moles, is that changing? No, the gas is not leaking, right? The container is not leaking. Therefore, N is constant, R is constant, and so let's write down the ideal gas law. So it says, let me write it this way: P final, V final is equal to N R T final, right? And then P initial, V initial is equal to N R T initial. That's the ideal gas law at the end, and I apply the ideal gas law at the beginning. I know P final, I know V final. I'm sorry. I know P initial, I don't even know them explicitly, I know their ratios. And I know explicitly what T initial was. The question is find T final. You have 2 equations, a bunch of things cancel if you divide the 2 equations by each other. So divide them. Divide this equation by this equation, right? That's math. And so you got P final over P initial. P final over P initial times V final over V initial is equal to, when you divide N over N cancels, R over R cancels, and you have T final over T initial, right? If I multiply both sides by T initial, or let's just leave it like T final over T initial, and I would like to find T final, so multiply both sides by T initial, and then solve. I trapped myself into a small space. Can I erase this side, this a little bit? Mm-hmm. Yeah, okay. So, here, you get T final is equal to P final over P final over P initial, V final, V initial, T initial, and let's see. P final over P initial. P final is 3 times P initial. So P final over P initial would be 3. V final over V initial, you get a half, right? Yeah, and this one is 273, right? and you do the math. Well,
1.5.
how many? 125 you said?
No.
Or let me copy this. I have 136.5. 136.5K. All right,
Would it
Ron?
be bigger than that?
Yeah, it wouldn't it be bigger
Like,
than
I think
that?
converting that to Celsius.
273.
Oh, did you convert back to Celsius? We've got 409.5 and 4.
Oh, yeah, so in K,
136.5.
yeah, so in K it's 136.5
In
K.
No, no, in
Pressure is
Celsius.
409K.
I got, it's 409K.
And then
Oh, I
Celsius is
switched it,
132.
409K, and then, yeah, you're right, thank you. Yeah, thank you. 409.5, I guess, right?
Yes.
And this one is 136.5? Okay, yeah. Thank you. All right, so that's that one. We talked about, yeah, so, ideal gas processes, what kinds of processes can we take an ideal gas to? You can compress the container, you can expand it. You can keep the volume constant, but you can put it in, you can add what's called heat to it. We'll talk about it in a moment. You can keep, so in other words, you can keep the temperature constant, you can keep the volume constant, you can keep the pressure constant. Those are three processes, and there are others. The process when you keep the pressure constant is called isobaric. When you keep the volume constant, isobaric. And you keep the pressure constant, isothermal. So let's get to, I have one example which has two processes. So you have a gas initially at 2 atmospheres of pressure. Again, atmospheres is not a good unit. We want to immediately change it to pascals, yeah. And it has an initial temperature of 200 degrees Celsius. And then it's expanded isothermally. Expanded means it gets larger. So here's the PV diagram. Here's P, here's P, and our gas initially, it was here at 2 atmospheres, right? It's at 2, I will change in a moment from atmospheres to the appropriate unit. And so it says the temperature at this step, let me call it step 1. The temperature here, let's call it T1. It is 200 degrees Celsius. Again, we will change those in a little bit. We have the pressure and the volume here, let's call it whatever it is, let's call it V. Then it says we expand it until the volume doubles. The volume is doubled. Isothermally. Isothermal means the volume will double here. The volume will be twice V. And it ends up somewhere here. Usually an isothermal curve looks like that. Because PV equal to nRT, right? PV equal to nRT, so the right side would be constant, nRT is constant, so the product of P times V is constant. So they are inversely proportional to each other, right? Yeah. So you got this. So this is the second part here. So the temperature here is still what? 200. And how do I know that? They said it's isothermal. Yeah, thank you. So you want like this. Isothermal. And then it says it undergoes, now once you get here, it undergoes an isobaric compression until it goes back to the original volume. Isobaric means what?
Same pressure.
Same pressure. So that we will go now this way. Isobaric until we get here. This is the third state. Okay? And basically the question is, what is the pressure and temperature at every step? Okay. So at step 1, the pressure is 2 atmospheres and the temperature is 200 degrees Celsius. At step 2, I know that the temperature is 200 because it's isothermal. okay? So let's find what the pressure is at step 2. Okay, at step 2. What is the pressure? So, I know that P1 is 2 atmospheres. And you know that 1 atmosphere is how many pascals?
780, 768,
760. I think you're measuring millimeters of mercury.
It's like 1.013 times 10 to the fifth.
10 to the 5th, yeah.
Something like that.
So it is this 1.013 times 10 to the 5th pascals for every 1 atmosphere. So twice this would be 2.026 times 10 to the 5th pascals. Pressure. The temperature T1 is 200 degrees Celsius, and that is 473. Please correct me if I get anything wrong. Just the temperature P2 we don't know. The pressure P2 we don't know. The temperature T2 we know. It's 473 K. Okay. So I'm going to write the ideal gas law. Yeah.
Just a question, with your PV graph, it should be curved, right? It's hard to tell from.
This is curved.
Yeah.
It's not a straight
Yeah.
line. Yeah, exactly. So 473, right? Yeah. So I know that T1 V1 equals to N R T1, right? And P2 V2 is equal to N R T2. Again, what do we do? Yeah, divide the 2 equations and cancel a bunch of things. So when you divide, on the right side, what do you get?
T1 over T2.
You get T1 over T2, and how much is that?
1.
It's 1. They're equal to each other. It's isothermal. The temperature at step 1 along this curve here, this isotherm, is constant. So you get 1. Yeah. So 1. On this side, you get P1 V1 over P2 V2, like so. And so we also know V2 is twice V1, right? The volume doubled. V2 is twice V1. So let's solve for P2. So P2 will equal to V1 over V2 times P1. And so V1 over V2, what is V1 divided by V2? 1/2, right? Yeah. And half of P1 is half of this number, right? So it's 1 atmosphere, or 1.013
013.
times 10 to the 5th pascals. The next one is what's the temperature now at 3? What's the temperature at 3? Well, what do you use? Which law? The ideal gas law, one more time. So you're going from step 2 to step 3, so you write the ideal gas law at step 2 and at step 3, and then you again divide them. And a bunch of things cancel. So that's right, we got P3, V3 equal to N R T3, and then P2, V2 is equal to N R T2. Divide both sides. So on this end is what's going to cancel on the left side.
Pressure?
The pressure, yeah. How do I know that the pressure at 3 is equal to the pressure at 2? Yeah, this one. It's constant pressure. Isobaric, yeah. It's constant pressure. So yeah, so the pressure at 3 and the pressure at 2 are the same because it's same pressure. Isobaric. So these two are going to cancel. So I got V3 over V2. The N and the R, they go away. And you have T3, T2. And so T3 will equal to V3 over V2 times T2. And you can plug in the first. What is V3 divided by V2?
1.
The volume at 3 divided by the volume at step 2.
1 over 2.
It's half, yeah, it's 1/2, right? The volume at step 3, the volume at step 3 is the same as the volume at step 1, right? They're the same volume. And this volume here is twice, so this one over this one would be just half, yeah. So 1/2. The temperature at step 2, how much is it?
200.
So should we plug in 200 degrees Celsius or?
470.
Yeah, plug in 473. It's always in K. 473. And what does this give?
236.5.
236.5?
Yeah, I think so.
Let me, yes, 236.5. Okay, and you subtract 273 and get minus 36.5 degrees Celsius, right? So if you plug 200 degrees Celsius, you would have ended up with T3 being 100 degrees Celsius instead of being negative, below freezing for water. So, yeah, always work with SI units if you're not sure. Okay. Oh, done with chapter 18. Okay. All right. So chapter 19, what is it about? It's about how to change the internal energy or the thermal energy of a gas, or a solid. So it talks about 3 things. So if I have an object here, how am I going to change the object, this object's energy? I can increase its temperature, but with mechanics, with Newton's laws, let's say, yeah, apply a force and do work on it. So if I apply a force, I can start moving my keys, give them some kinetic energy, or lift them, give them some maybe kinetic plus some potential energy. So now we're going to ignore the mechanical energy in this chapter. We're interested in the internal energy that's inside. So if you have a gas tank, right, a gas tank, if I take that gas tank and just throw it, the whole gas tank will have some potential energy, some mechanical potential energy, and it will have some kinetic energy. I'm not interested in that. I'm interested in a gas tank that's just sitting here, right here, and it actually does have energy. Why? Because I'm interested in what's inside it, what makes up the gas. All the little molecules moving around. And actually that is the energy. If you take all the constituents and add all those little kinetic energies for every atom and molecule, that would be the thermal energy. For a monatomic gas at least, okay? So that's what we're interested in. And the question is, how do I change the thermal energy of these molecules? How do I make them move faster or slower? And the answer from the first law of thermodynamics, it will tell us 2 things. I can do work on them by taking that piston and compressing it or expanding it. Or I can put it on a stove or put it in thermal contact with something cooler or hotter. If I put it in contact with something hotter, energy will flow from the hot object to the cool object until they come to thermal equilibrium and they have the same temperature. It never goes the other way around. Otherwise, the cooler object will keep getting colder and the hotter object will keep getting hotter until every single time the cool will get cooler and the hot will get hotter. It doesn't happen. So they just come to some temperature in between their temperatures. That's called heat. The energy that flows because of a difference of temperature, that's called heat. And then the work done is actually work that you use a force to compress the gas. I'm not talking about the force to make the whole tank of gas move. I'm talking about the force to change the volume of that gas, to make it smaller or bigger. And so the first law of thermodynamics says if you add the work done on this gas and the heat that you give the gas or take away from it, that's equal to the change in its thermal energy. That's it. That's the first law. And we're going to play with it. So let's work with the work first. Work with the work. So we will deal with the work done on a gas and then the heat. And fortunately, or maybe I don't know, our book is unique. It discusses the work done on a gas instead of the work done by the gas. They're equal in magnitude, but they have opposite signs. Every other textbook I've seen, they always talk about the work done by the gas. And there will be a minus sign difference. If you have a different textbook, there will be a minus sign in the first law of thermodynamics. So when I say the work done, oh, here's even what's more unfortunate. 2 chapters later, the author switches his mind and then says, oh yeah, let's deal with the work that we will mean by W, we will mean the work done by the gas, not the work done on the gas. Okay. So let's take that. So we're in chapter what now? 19, yeah. I think it's titled work, heat, and the first law. And we will do them in that order. Work and then heat. Work, heat. And when I say first law, I mean first law of thermodynamics. Thermodynamics. Oh. So here is a gas, and I'm going to orient it horizontally, so we ignore any gravitational effects. Here's my gas. It's in a cylinder. Again, always you have a cylinder. That's the theme. It's a cylinder, and or a piston here. The cylinder is a piston. So what I'm going to do is push on the gas. If my push, if the pressure I apply, or the push I apply, is stronger than the push of the gas will compress. But if the gas may be really hot, I can push, but it expands regardless of my force. Yes. So let's say I'm going to apply a force this way, and let's say the piston here has an area A, a cross-sectional area A. It's cylindrical. You can get more complicated shapes if you like, but it's always a cylinder. That's good enough. It gets the point across. So I'm going to apply a force. If my force does not move the piston at all, how much work have I done? 0. Yeah, I mean I can do this all day. I get tired, but I'm not doing any work. Yeah. So I'm going to push it, and it will compress a little bit. It will compress by an amount, let's say, delta x, or dx. So how much work have I done? Work is what?
F dx.
Yeah, it's force times the displacement. In this case, everything is, there's no theta, cosines, or anything. So it would be just the force times dx, right? I should call it dw, by the way, because it's a small amount of work, dw. Now the force is the pressure times the area. Because remember what pressure was? It's force divided by area. So force is pressure times area. Yeah? Okay. So the force would be the pressure times the area times dx. That's the work, dw. Is my work positive or negative if I cause I cause the displacement in the same direction as my force? It's positive work, yeah. Because remember, it's FD cosine theta, and cosine theta in this theta is 0 degrees, right? You push this way and the motion is that way, so they're parallel to each other. So it's positive. So, but what is this in relation to the volume of the gas, or the change in volume? What's the volume of a cylinder?
Or pi r squared, right?
Yeah, it's the area, pi r squared, that's the area of the circular thing, if it's circular, times the height. So the circular thing is the area, A, and then the height is dx. So this is a small amount of volume. So it's dV, d volume, it's a small amount of volume. This is the volume, dV. So P times dV, but I have to put a minus sign, why? What happened to the volume when I decrease? The volume decreased, but the work is positive, right? If the volume decreased, what sign does the volume have? The change in volume. Negative. To make it positive, what do I do?
Add a negative.
Yeah, add a negative. And that's an amount dW. Now this works even if the change in volume is positive, meaning it actually expanded as I'm pushing this way, it means the work I've done is negative. So this works in both cases. Okay? So this is the amount of work. And so the total work done would be negative P dV. This is the work done on the gas. The work done on the gas. The work done by the gas. See, the gas is pushing you, and you're compressing it. So the work done by the gas, if it's getting compressed, the work done by the gas is negative. If it's expanding, if it expands, it means the gas has pushed the piston away, and so it caused the displacement in the direction it wants to push it. That's positive work. Okay. So this W here, that's right. Yeah. Work done on the gas. So if you plot, P is typically a function of V, right? Because you can just evaluate this integral, right? Because if I say integrated, what would you say? I need to know what P is. Is P constant? Does it depend on V? And if it does, in what manner? And we will study the three cases that we have. In fact, there are four cases. One of them is adiabatic, where there is no heat. But we will study three cases for now, and then toward the end of the chapter we'll do the other. So, in other words, here's P, or here's V, and here's P. We always draw the PV diagram. And so let's say I took my gas from here to here, right? So would this be, so the gas initially is here, and then at the end it's here. Did I do a positive amount of work, or did I do a negative amount of work?
A negative.
Yeah, the gas expanded. The integral, this area here is what? What's this area? It's the integral of what? Integral of P dV, right?
Yeah, dW.
So you can think of this like f of x, and this is x. The integral of f of x with respect to x is the area. And but there is a minus sign. So if the area is positive, the work done is negative. Yeah, so,
Can you go over why you added that negative again?
yeah. So I said, I know when I push the piston this way, I'm doing positive work. Because I'm pushing it this way and the piston is displacing this way. So my work is positive. But if I'm going to put this in terms of the volume or the change in volume of the gas, I have to put a minus sign. Why? Because what happened to the gas when the volume shrinks? The change in volume is negative, right?
Yeah.
Because the final volume is less than the initial volume. So this technically has a negative sign, so you need a minus. So it's just to make things right. Yeah.
So the reason like we're doing it from the perspective of volume is because you're doing work on the system right now, right?
Yeah. So we're. Why do I why do I talk about the volume, right?
Yeah.
Yeah, typically because we have the ideal gas law, and the ideal gas law talks about the volume of the gas, right? So yeah, so we, in terms of the volume of the gas, That's why I transferred.
Earlier you were mentioning over the book it says by the system and on the system, that changes the sign.
Yes, so this is the work done on the system.
Right.
Yeah, this is the work done on the system. And the work done by the system will be the negative of that. And the reason is, of course, by Newton's third law, because you apply force, you get a force back on you. So that is that, PDG. That's good. We have some time. Notice the work done depends on the path you take. If I tell you this, here is V, and here is P. Here, the gas initially had some pressure, and it had some volume. And I say the gas went from this pressure and volume to maybe this pressure and volume. So this is the initial, this is the final. And next I calculate the work. Can you? Or can you not? No. Why not?
You don't know the pattern.
We need to know the path, yeah. Maybe I went isobarically this way, and then isoporic this way. That's one way. And in this case, the area is just here. It's just this tiny area. Or maybe I went this way. Isoporic this way, and then I went this way. In this case, this is the area, bigger work. Yeah, or any other path. Maybe I went straight this way, I don't know, or any other thing. So it depends on the path. The work done depends on the path. Okay. So talked about that. So let's discuss. Let's give an example first, and then we will discuss. I mean, it's a simple example, but let me try to draw it where we get some practice calculating. So this is the volume in centimeters cubed, and this is the pressure in kilopascals. Right? Kilopascals means thousands of pascals, right? So this is 100, 200, 300, 100, 200, 300, and this is here, 500, 1,000, and 1,500. Like so. And I'm going to show you what the initial was. The initial was one like this. This is initially where it was. And then it took this path. One like this. And then it went isobarically this way. This is the final state. And the question is, first, is the work done on the gas? The work done on the gas, is it positive or negative, the work?
On the gas, is negative?
Yeah, it's negative, because the area is positive. Yeah, the gas is expanding. That means you have done negative. The gas did positive work, it expanded, it did what it wants. So the question is, how much work? What would you do?
Calculate density.
Yeah, calculate